Hello and welcome to this 9th lecture. This is for the class Introduction to Artificial Intelligence and Machine Learning for Engineers. So today what we are going to talk about is artificial neural network and deep learning. So we are still talking about machine learning. So machine learning is a subclass of artificial intelligence, and specifically we are still talking about supervised machine learning, where your goal is to find a way to map some input X to map them into Y. So you want to predict a given observation Y as a function of some feature X. So this is supervised machine learning because in this case the data are labeled. So what we saw last time is linear regression, and we talked about linear regression, we talked about polynomial regression, which is a special case of linear regression. We talk about multivariate regression. So this is one possible algorithm for supervised machine learning, where you assume that the relationship between the input and the output follows just a linear function. But in many cases, although linear regression can work in a lot of problems, in some cases it's just not complex enough. Like it's not going to be a very efficient method when you have a very complex relationship between the input and the output. So in those problems, when you end up with some problems that do not really rely on a linear relationship, some problems that are intrinsically non-linear, then linear regression will not be a good choice, or polynomial regression will not be a good choice. And in this case, a very efficient and very powerful technique is to use artificial neural network, or ANN. And these types of techniques can really allow you to fit very complex model that can interpolate very complex relationship between a lot of inputs and one or several output. So the cases where artificial neural network is really going to be beneficial as compared to linear regression or to lasso, for example, is in the case of a non-linear model. And by non-linear model, what I mean is when you have a non-linear hypothesis. When the hypothesis of your model, the way you map X into Y, if this is governed by a non-linear relationship, a non-linear function, then potentially artificial neural network is going to be a better choice than linear regression or than lasso. So when we used linear regression and polynomial regression, the way we solved this issue is by doing some feature engineering. So the way we transformed a linear problem into a non-linear problem while still using linear regression is to start with your input, for example, x1, x2, x3. Those are the different features of your model. And then to create some new features based on those initial features that you have to do some feature engineering to create some new features that are some mathematical transformation. So for example, like if you want to transform a linear into a non-linear problem, the first thing that you can do is to introduce some quadratic features. For example, you can say x1, you're going to also transform it into x1 square, and you are going to add to x1, x2, x3, you're going to add x1 square. And now your model will be a function of not just x1, x2, x3, but also of x1 square. So now your model, even though it's still a linear model where x1 square is just one new feature that's going to be linearly related to the output, now the model will become non-linear because you have created those new features that are some mathematical transformation of the initial features. So in this case, if you just focus on quadratic features, so you would create the square of x2, you would create the square of x3 as well. But in this case, you would also need to create the cross terms. You will need to create the term that is x1 times x2, the term that is x2 times x3, and the term that is x1 times x3. So altogether, you see that even if you start with just a limited number of features, and even if you just transform it into quadratic features by taking the square or the cross product, you can really increase quite a lot the number of features. And here we are just taking the example of a quadratic transformation, but there is a whole kind of other range of mathematical transformation that you could use. You could take the square root of the features, you could take the exponential of the features, you could take the log of the features, or usually we take the log of 1 plus the feature. You could take the inverse of the feature, etc. So there is a whole kind of mathematical transformation that you can do. And when you have just a few features like this, then it's possible to just transform them to create some new features that are just going to be some mathematical transformation that will allow you to have now a nonlinear model that does not only depend on the feature but also on their mathematical transformation. So you can end up with very complex model if you do this, but the problem is that the number of features that you will have will really become very, very large if you try all those combinations. Like the number of features that you can create is virtually infinite. So you can certainly do that, but it becomes non-manageable. It becomes non-realistic to use this when you start to have lots of features. When you have a lot of features to begin with, it's not practical to multiply even more, to demultiply the number of features. Like you can really end up with too many features. And the problem when you have so many features is that you start to have a very complex model with a lot of parameters, and to train this model you will need a lot of training data. Just as a general rule of thumb, like you cannot have more parameters than training data. If you have more parameters than training data, then you cannot uniquely decide what is the value of the parameters. You need to have more training data than parameters that needs to be optimized. Just like when you have two unknowns in mathematics, then if you want to find the value of those two unknowns, then you need at least two independent equations. So here it's the same idea. The more parameters you want to fix, to optimize, the more training data you need. And sometimes you just don't have that many training data. So you need to focus on models that are more simple. So here, one of the main advantage of the artificial neural network techniques that we are going to talk about now is that it can create its own new feature. It can start with the feature x1, x2, x3, etc. And based on those features, it's going to combine them on its own in a smart way without the need for you to decide how you should combine those features. And it's going to create on its own some new features that hopefully are going to be useful to predict the output. So if it thinks that x1 and x2 need to be combined to each other to create a new feature that is more useful, that is more relevant to predict the observation for the specific problem that you are interested in, then it can create on its own those complex new features. And that's a great advantage over linear regression, because in this case, it means that you don't have to do that much feature engineering. You can still create a new feature if you want, but the artificial neural network will attempt to do this on its own. And it's a very powerful technique because it can just combine all the features in very different way, maybe very non-intuitive way that you would not have thought yourself otherwise, but ways that are going to be very useful to predict the output of the model. So the main idea of an artificial neural network is that it try to mimic in a fairly loose way the way the brain is working. So it looks like the way the brain is working, like the analogy is not perfect, like the brain, not on first we don't necessarily understand fully how the brain is working, so it's not an easy task to try to mimic it. But even based on our present understanding of how the brain is working, it's not exactly working like an artificial neural network. But nevertheless, that's that's where the inspiration came from. So if you take a neural network, so there is those two words that are important. There is neural. Neural means that you will have some neurons. So just like in the brain, you will have some cells, some neurons that are going to be some small computing units. And then you have a network. A network is when you have some nodes. So in this case, the nodes are the neurons. And then you have some connections between those nodes. So just like a mechanical truss, a structural truss, where you have some nodes that are connected by some joints, this forms a network. You have some nodes that are connected to each other by some constraints or some connections. This is a network. So if this is a network, it means that you will have some connections between the neurons, between the nodes of the network, between the neurons. So those two things are important, like how many neurons will you be using, and how many connection in between them, and what will be the nature of those connection, what will be the nature of the overall network. Those are two very important things when you build a neural network. So the overall architecture of the neural network is going to look like this. First, you will start with your initial features. So let's assume that you have three features, in this case, x1, x2, and x3. Those are going to be your free input for the model. This is what you know, the features. This is what you know from the training example. And based on this, what you want to do is to predict a given output. You want to predict a given observable y, and your goal is to find a way to map those features into this output. This is what you do in supervised machine learning. So in artificial neural network, those input here, this is going to form a first layer of neurons. So this is going to be your input layer. So a layer is going to be just an ensemble of neurons that are on top of each other. So here you will have the input neurons, where you have the feature of your model, the feature that you measured, the feature for the training example that you have. So this is going to be the first layer, and then on the other side of the network, you will have an output layer. In this case, I have indicated only one output y. In many cases, you just want to predict one number, but sometimes you can have a network that have two numbers, two neurons in the output layers, or 3 or 4. Like you can predict several quantities at the same time. For example, if you wanted to predict some properties of concrete, you could say, I'm going to build one neuron that is going to predict the 7-day strength, the strength after 7 days, the strength of the concrete after 28 days, the strength of the concrete after 120 days, or other properties of concrete, like the slump of concrete, or like its density, or whatever other properties you can think of. Like you can list here in the output layer, you can list the different properties that you want to predict. Okay, but in many cases, we just want to predict one thing at a time. So very often there is only one neurons in the output layer, but it's not necessarily the case. You can have more than one neurons. So this is going to be the output neurons. So those are going to be the observations. This is what you want to predict. And in between, you want your network to find a way to map the input to the output. And the way this is going to work in an artificial neural network is that you will have some additional neurons that are going to be within an additional layer that we call the hidden layer. it's a hidden layer because it's a layers of neurons that are hidden from the model. When you look at the model, you provide to the model an input, which is the features, and it's going to provide you an output, which is the observation. And then somewhere in between, somewhere inside this black box, there will be some hidden neurons that you cannot or that you won't see directly. Of course, you can see those hidden neurons if you look into inside the structure of the artificial neural network, but it's hidden because you don't see it when you provide the initial value for the features, and you don't see it when the model just gives you the output. It's something that is inside the network. So this is what is going to be called the hidden layer. And this hidden layer is going to be made of hidden neurons. And here you can have an arbitrary number. Here I drew 4 hidden neurons, but you can have more than 4. You can have 1, 2, 3, 4, 5. Like you can have any number that you want. And again, like depending on the number of neurons that you use, your model can either be underfitted or can be overfitted. So it's a similar idea than in the case of polynomial regression. Like the more hidden neurons you will put, the more you have a risk that your model will become overfitted because it becomes very complex. And on the other hand, if you put too few neurons, then your model will not be able to properly interpolate the relationship between the input and the output. So potentially your model can become underfitted. So again, you will need to find the best balance between underfitting and overfitting by adjusting the number of neurons. There is another thing is that in some networks you can also have more than one hidden layer. You can have several layers of hidden neurons. So in this case, when you have more than one hidden layer, this is where we start to talk about deep models. Deep means that it has more than one hidden layer. And in this case, when you start to talk about deep models, then this is what we typically call deep learning, when you have more than one layers, when you have very deep model that has several layers. And so the way an artificial neural network works is that, so you have this input layer, and each of those features here will be a given neurons, and those neurons are going to be connected. Each neuron is going to be connected to each of the neurons of the hidden layer. So the input neurons are not directly connected to the output. They are connected to the hidden neurons within the hidden layer, and each of the neurons in the input is connected to all of the neurons in the hidden layer. So we're going to see in a few seconds what those connection means. But again, it mimics the brain, where you have some inputs, some neurons that are connected to other neurons with some synapse, some dendrites, etc. So it mimics the way the information can be communicated from one neurons to the next within the brain. And then once the information of the input layer is going to be transmitted to the hidden layer, you will have some mathematical operation occurring within the neurons within the hidden layers. They are going to provide an output signal, and this output signal is going to be transmitted to the neuron of the output layer, which again is going to combine and process all those signals, and based on this make a prediction of what is the output of the model. So so the main idea of this artificial neural network is again to create a network where each layer is going to transmit some information to all the neurons of the next layers. Those neurons are going to combine this information in different ways, and based on this will either transmit the signal to the next layers, or maybe not transmit at all the signal. We just block the signal and not transmit it to the next layer. So this is going to be the main idea of artificial neural network, to have a system of those neurons where each neuron takes some inputs from the neurons of the previous layers, and then will either transmit or not a signal to the next layer. And the main reason that the artificial neural network is so useful is that it does not directly try to link the input directly to the output. It's going to first take the input, combine them in different ways in order to create some new neurons. Those neurons are going to be some new features. So this is at the stage where it's going to create its own new features. Those are going to be the new feature that it thinks are useful to be able to predict the output. And then those new features are going to be used to predict the output. So rather than directly going from the input to the output, it's going to first combine the input together into creating some new features, some combination, some mathematical transformation of the initial features, and then use those new features to create, to predict the output. And those new features are going to be more useful to create to predict the output than the initial feature that you provided. And that's the main interest of the artificial neural network. It just creates on its own some new features without requiring any intuition from you or any input. It's just going to create on its own without any external guidance the feature that it thinks are useful to predict the output. So if we look a little bit in more details, if we zoom on a given neuron, so in the case of an artificial neural network, we would call the different neurons, we would call them artificial neurons to distinguish them from real neurons. And if you look at a given neurons in the hidden layer, the way it will work is that each neuron is going to be a small processing unit. It's going to do some mathematical operation. It's going to take some inputs, which are going to be the input from the previous layer, the previous neurons. In this case, if you take something in the first hidden layer, then it's just going to use the initial features, which are going to be in the previous layer. It's going to combine those features in a smart way. And then based on this, it's going to give you an output signal, which is not going to be directly the output of the model. It's just going to be the small output of each neuron. So each neuron is going to be a small regression model. It's going to be a small processing unit that takes some input signal, a connection of a small signals, and is going to give you in return an output signal. So, and this output signal is going to be the small signal that is generated by this output, which typically we would write g of x. G of x is going to be the output signal that is generated by a given hidden neurons. So in that sense, it works pretty much like a neuron in the brain, where you have some electric signal that are used as input to the neurons, and depending on the value of those electric signals, this neuron is either going to transmit a signal as an output or not transmit any signal at all. So now let's look a little bit in more detail how a given artificial neuron is going to take those input, combine them, and create a given output. So for this, let's take an example where, again, let's take one input in the hidden layer, the first hidden layer. So let's assume that you have three features like this in the previous layer, which in this case is the input layer. This is the layer that is just before the neurons that we are considering. So those inputs are each of them is a different neuron. So you have as many neurons as you have features. So the first thing that the neuron is going to do is first to take the value of each of those 3 neurons. So the value is going to be the value of the features. In your training example, every time you have a training example, you have all the features x1, x2, and x3, and it's related to a given observation. So for each of the neurons, the input neurons, you are going to use the value of the features. And the first thing that the model is going to do, the first thing that this given neuron is going to do, here we are just going to talk about one single neuron, and then those neurons are going to be connected to each other in the network. The first thing that this neuron is going to do is to take those input from the previous layer and to multiply each of them by a given weight, theta 1, theta 2, and theta 3. So you multiply all those input by the value of those input by a given weight. So those are some weights. You are just going to multiply the value of the previous neurons by this weight. Then what you are going to do is to take all of those weights and you are going to sum them all. So you're going to take the sum of all the input layers multiplied by their own weights. So you're going to take each value for the input layer, multiply it by the right weight, and then take the sum of all those weighted inputs. So once you have created the sum of those weighted inputs, you have now a new variable z. And the last thing that the neuron is going to do is to feed this variable z into a nonlinear function that we are going to call an activation function. So it takes its sum of the weighted neurons and then it's going to feed that into an activation function. So a function that may look like this, a function that will use z as an input and will be a function, for example, a g of z. So this is going to be an activation function. It's going to transform z in a nonlinear fashion. So it's just a mathematical transformation. And then based on this, you will get the output signal of this neuron, which is g of z. And so this thing here, this entire thing, is what the neuron contain. Like those different elements is the content of the neurons. So in this case here, everything that is below this, those are the previous neurons. After this is the output that is given by these neurons. But everything, the weight, the sum of those weights, and the activation function, this is what is contained between each neuron. Each neuron is this small processing unit that is doing this operation. So there is one thing that we will need to add. So it's not the full structure of the neuron just yet, but let's just try to understand what this neuron is doing. So first, it's taking the input neurons, the neurons from the previous layers. It's going to give a given weight to each of those neurons, and then it's going to combine all the previous neurons with their weighted, with their respective weights, combine them together by doing a summation. This gives you a new variable z, and then depending on the variable z, depending on the value of z, if z is very small, then the layer will not transmit any signal. Like if z is very negative, very close to minus infinity, or very negative, then there will be nothing that will be transmitted by this neurons. It's going to be equal to 0. The output signal of this neuron is going to be equal to 0. On the other hand, if z is very large, then you will have a lot of signal transmitted by this neuron. Like this neuron is going to transmit a signal of, for example, +1. So it means that depending on the value of z, depending on the value of the input signal, the neurons will either transmit an output signal or not transmit any output signal. So there is one thing that we need to add for this, which is for given neurons, how easy will it be to transmit, to activate these neurons? When these neurons transmit this signal, we will say that this neuron is activated. It receives enough input signal so that it's going to transmit a given output. And so we need to add an extra parameter which tells how easy it is to activate these neurons. Is it going to be activated for a very large value of z, or for a very low value of z will be enough to activate it? So for this, we are going to add an extra parameter which captures how easy is it to activate this function. And the way we are going to do this is to add a bias. A bias will tell you roughly what is the threshold value that you need to exceed when you combine those input. When you multiply them with the weights, you take their sum. What is the threshold that you need to exceed? In this case, so far, the threshold is just 0. If z is larger than 0, you will have a lot of signal being transmitted. If z is lower than 0, you will have not so much or maybe no signal transmitted at all. So in order to tune the ability of a given neurons to transmit the signal or not, we need to add a bias. The bias will be roughly the value of the threshold that you need to exceed. So the way you are going to encode this bias is to add an extra neuron here, which is just going to be a bias unit, just a bias. It's just always equal to 1. 1 is the value of this bias. Then you are going to multiply this bias by another weight, which we are going to call theta naught, and then this weight is going to be added to the summation, which means that now, depending on the value of theta, if theta is very large, it means that, for example, if you take, let's zoom in on this activation function here. So if this is the activation function g of z, so the function will typically look like something like this, where it goes between 0 to +1. It's not always the case, but very often it's like this. It means that if you start for a given value, let's assume that this value is what you would get when you just sum the inputs with their weights. So if this value is the sum of the given input xi times their weight theta I, and then we sum this for all the input x1, x2, and x3. So this is what you would get without, if you had no bias. Let's assume that this gives you this value. Now we need to add the bias, and depending on the value of the bias, for example, if theta naught is positive, then it means that it's going to make it even easier to activate the neurons, because you will add a positive bias, which means that it will be easy for your z value, where z is going to be the sum of theta naught plus the sum of the xi theta I. When you add a positive theta naught, you will make it easier for the value z, which is the input in this case, to be large enough to activate the neurons. On the other hand, if theta naught is negative, and if theta naught is very negative, then you will make it much harder to activate this neuron. So you will, when you calculate the sum of theta naught plus the sum of the xi theta I, you will need a very large value for the input xi times theta I in order to generate a variable z that is large enough, because you make it very hard to activate these neurons, because it has to overcome a very negative bias. So it means that now, to activate these neurons, you will need for your input to be large enough to overcome the negative bias before it can start to activate this neuron because before these neurons will start to transmit a signal. So this bias here, depending on the value of the weight theta naught that you are using, a large theta naught will make it very easy to activate the neuron. It's going to be a very sensitive neuron. Every time it receives a small signal, it's going to transmit a given output. And if theta naught is very negative, then it's going to be a neuron that is very hard to activate. It will take a very large value for the initial input and for the initial weight to be able to overcome the bias and eventually to have an output signal to activate these neurons. So this is the entire all the steps that goes within one neurons. You sum all the inputs, you weight them, you add, you sum them all, you add a given bias, then it creates a new variable z, then you transform this variable z with a nonlinear transformation that looks like this, where if z is too low, the neurons is not going to be activated. If z is high enough, and in this case, if it's larger than 0, then the neurons will be activated. And based on this, you will get a given output. This neuron is going to give an output signal, and this output signal is going to be transmitted as an input for the neurons in the next layer. Each neuron will take some inputs from the previous layer and will generate some outputs that will be used as input for the neurons of the next layer. So the last step of each neuron is to take this variable z, which is the weighted sum of the inputs from the previous layer plus the bias, and then to fit that into an activation function. So this activation function is really what allows artificial neural network to map complex nonlinear relationship between input and output, because otherwise, when you just take the sum of the weighted input, this is exactly the same as a linear regression. You just do a linear combination of the input. So if it was just this, then the artificial neural network would be just the same as a linear regression model. So in order to be able to generate some non-linearity, to capture some non-linear relationship between input and output, you need to take this variable z and transform it into a non-linear new output, which will either activate the neurons or not. But in any case, you will get a response that is a non-linear response, something that is a non-linear function of the input z. And so this is dictated, this is governed by the activation function. So when you build an artificial neural network, you can choose the activation function that you want to use. There is different possible choice for the activation function, but usually it needs to be a nonlinear function. Otherwise, you are just doing linear regression. But for different problems, different types of activation function might be better suited than others. It depends on each problem. So let's see just a few examples of common activation function. The first one that was very much used initially, but it's a little bit used nowadays, is the sigmoid function. So the sigmoid function is based on this function. It's actually the function that governs the growth mechanism of many things, including the number of people that become sick due to a given sickness over time. And this sigmoid function takes the form of 1 over 1 plus exponential minus z. So this function, if we plot it, it looks like this. So z can always go between minus infinity to plus infinity. And then we plot the response of the neurons as a function of z. So when z is very negative, then exponential minus z will become very large. Like minus z will become very positive. So exponential of a very positive number will become a very large number. So the exponential will win over 1, and so you will basically take 1 over a very large number. So in this case, the sigmoid will just be equal to 0. So when z is very small, very negative, the sigmoid is basically equal to 0. On the other hand, when the value of z becomes very large, very positive, then exponential minus z becomes very close to 0. It tends to 0. The limit would be 0, which means that in this case, when z becomes very large, you get 1 divided by 1. So it gives you a sigmoid will tend towards the value 1 at very large value of z. And in between, so it's going to be a monotonic function that increases with z. When z equals 0, exponential of 0 is equal to 1. So you get 1 divided by 2. So when z is equal to 0, then the value would be 1/2 or 0.5. So the sigmoid function looks like this. Initially, it's very flat. Then when z starts to be close to 0, you have an exponential increase, so which is what you have at the beginning of pandemic, for example. Initially, the number of cases is increasing exponentially with time, and then at some point, when the growth starts to saturate, when all the population have become sick, then there's nobody else to infect, then the growth starts to decrease, and then you end up with a function that just reaches a maximum like this, and it just saturates at 1. So this is the sigmoid function. It's again, it's not so much used anymore, but it was very used initially when the first artificial neural network were developed. And it's always a good choice to still try if this how this sigmoid function is working. So again, in this case, the outcome of the sigmoid function dictates whether the neuron is going to be transmitted some signal or not. If z is very large, then the neuron is going to be activated and going to transmit an output signal. If z is very small, then there is no signal being transmitted by these neurons. And in between, when z is close to 0, then you have an intermediate signal that is being transmitted, which is a non-linear transformation of z. Another example of a simple activation function that is actually a little bit more closely mimicking the way it works in the brain is to use a step function, which is also one of the function that was initially used in artificial neural network, but is very rarely used nowadays, which is in this case to say that the value of the activation function is going to be +1 if z is positive or equal to 0, or is going to be equal to 0 otherwise if z is negative. And so the main idea in this case of this step function is if you plot it, it just looks as a Heaviside function. So if z is negative, then there's nothing that is being transmitted, like the neuron is just completely blocking the signal. It's going to be equal to the output is just going to be equal to 0. There is no signal being transmitted, and as soon as the input signal reaches a given threshold, which in this case would be 0, then suddenly the model becomes this neuron starts to generate an output signal. So in this case, it's like a shrinked version of the sigmoid. Like if you were to shrink this sigmoid so that it very quickly switch from 0 to 1, then if you shrink it infinitely, then you end up with a step function that just directly either passes nothing as an output signal or just passes +1. And in this case, it can just generate 0 or +1 and nothing else. There is no other signal. It doesn't depend on the exact value of z. So again, this types of activation function is not so much used in practice anymore. Another example that is more commonly used is the ReLU activation function, where ReLU stands for rectified linear unit. ReLU, rectified linear unit. And so in this case, the ReLU function is like this. The output of each neuron is going to be the maximum of 0 or of the input variable z. So if you plot this function, this is how it would look like. So z is still the input variable. The output is still g of z. So when you look at what this function is doing, as long as z is negative, then the maximum of a negative value n of 0 is going to be 0. So in this case, as long as z remains negative, then the neuron is not going to be transmitting anything. There will be no signal being transmitted as an output. And as soon as z becomes positive, then the maximum of 0 and z becomes equal to z. Z is larger than 0, so the maximum of those two numbers now become z, which means that this function is just going to basically just give you as an output 0 if z is smaller than 0, and will just give you back the same z if z is positive. So in this case, the function is just going to look like this. As soon as z becomes negative, it gives you back exactly the same z. So it looks like this doesn't look necessarily very useful, because it just gives you back exactly the same input. But the main value of this is this nonlinear behavior, that the neurons can either block the signal or transmit the signal depending on the value of the signal, depending on whether it exceeds the threshold or not. So this is what is creating a nonlinear dependence. So this is how you can have an output that is a nonlinear combination of the input, depending on whether this input z is exceeding the signal or not. It's going to activate this neuron or not, and this is what is generating the nonlinearity in the model. So when you build an artificial neural network, you will have to choose what is the activation function that you want to use. You can either use the same activation function for all the neurons, or decide that certain neurons will have certain types of activation function and other neurons will have other types of activation function. But usually, as a first start, it's good to just start with all the neurons having all the same. So I would recommend the ReLU function, just because it's now pretty commonly used nowadays. So it's a very powerful activation function that works in many cases, but nevertheless, in some cases, maybe a sigmoid function or other types of function, like a hyperbolic tangent or other type of activation function, can be useful. So if you look at, for example, in MATLAB, you have different choices for the activation function. So when you build your artificial neural network, you will need to pick as an option the types of activation function that you want to use. And again, there's no right or wrong answer. It really depends on the types of problem that you are dealing with. Each problem will have its best activation function. So if we try to summarize how the overall network is working for an artificial neural network. So let's take an example. For example, if again, let's take just 3 given input variables. So let's assume you have x1, x2, and x3. Those are your 3 input neurons. So then those input neurons are going to be connected to some hidden neurons. So for example, let's assume that there's going to be 3 hidden neurons, but again, this can be 2, can be 4, etc. Like the number can change. And then those hidden neuron is going to be connected to an output, to either 1 or more than 1, 2, 3, several output. Those are the output that you want to predict. So usually in terms of name conventions, so we are going to write the input that are in the hidden layer. This is in this case, the first layer, the second hidden layer. Then you have the third, which in this case is the output layer, and then the first one is just going to be the input layer. So the first one, typically each of the neurons of the first input layers, so rather than just calling them x1, x2, x3, what we are going to do typically is to call them A with a given subscript that is going to be the number of the layer that they belong to, and so a superscript that is the number of the neurons that the number of the layer that it belongs to, and a subscript that is the number of this neuron within this layer. So this first layer will be A11. It belongs to the first layer, and it's the first neuron of this first layer. This one would be A12. It's the second neuron of the first layer, and this one would be A31. It's the third layer of the third neuron of the first layer. And then the hidden neurons, we're going to write it in the same way. Now this is the second layer. So in this case, this is the first neuron of the second layer. This is going to be the second neuron of the second layer. And this is going to be the third neuron of the second layer. And then the last one in this case is going to be the first neuron, but in this case that would be the only one of the third layer. So then the other unit that we need to add is the bias. So you have the bias here. You will have another bias here. So those are the biased units. And now those things are going to be connected to each other. So the first layer are going to be connected to the second layer. The neurons for the first layer are going to be connected to the neurons of the second layer. Then the second layer neurons are going to be connected to the third layer neurons. The neurons for the first layer are not directly connected to the neurons of the third layer. Similarly speaking, the neurons of the second layer are not connected to each other. Like the neurons 1 from the layer 2 is not going to be connected to the neurons 2 of the layer 2. So the only thing that you have is connection in between two successive layers. So for example, you will have one connection here between this bias and the first neuron for the second layer. You will have a connection here, a connection here, a connection here, etc. And so each of those connections, so as a reminder, each of those connections comes with a given weight. Every time two neurons are connected together, they are first weighted and then they are summed all together. So the important feature, the important parameters of an artificial neural network are going to be the values of those weights. So we're talking about the value of the weights theta, because those theta values are going to define how strongly connected are each pair of neurons. Some neurons are going to be very strongly connected to each other. They are going to be associated with a very high value of theta, and some neurons are going to be only weakly connected to each other. So this is going to be important because it's going to dictate how strongly the output from one layer is going to be transmitted to the next layer. So in this case, in terms of notation, so the theta, the parameters theta that are connecting the first layer neurons to the second layer neurons, we are going to call it the theta 1 because those are the weights of the third layer. And then we are going to put as a subscript the numbers of the two layers that are connected to each other with this weight. So for example, this coefficient theta is connecting the bias of the first layer, which is index 0. It's connecting this to the first neurons of the second layer. So we are going to write this weight as theta superscript 1 because it's from the first layer, and then it's connecting the unit 0 of the first layer to the neurons number 1 of the second layer. So we are going to write this weight theta superscript 1 subscript 1 0. Similarly speaking, if we take the second one, this is going to be a coefficient theta associated to the first layer, associated to the neuron x1 of the first layer. In this case, it's connecting the neuron 1 in the first layer to the neuron 1 in the second layer. Same thing, this one is going to be the theta of the first layer. It's connecting the neuron 2 in the first layer to the neuron 1 in the second layer. And let's do one last one. This one is going to be theta 1. It's connecting the neuron 3 in the first layer to the neuron 1 in the second layer. And then, so it's going to be the same. For example, this connection here is going to be associated with a weight that is still theta 1 for the first layer. In this case, it's connecting the neuron 3 in the first layer to the neuron 3 in the second layer. And then, so we are going to do the same for the connection in between in between the second and the third layer. So every time you have a pair of neurons, you will have an associated weight. For example, this one is going to be now the weight associated to the second layer, and this weight is connecting the first layer in the third layer, the first neuron in the third layer. It's connected to this one is connecting the layer number, the neurons number 0, the bias of the second layer, to the first layer and the first neurons of the third layer. This one is still in layer number 2. It's connecting the first neurons of the second layer to the first neuron of the third layer. This one is in layer number 2, and it's connecting the second neurons of the is connecting the second neurons of the second layer to the first neuron of the third layer. And this one is another weight associated to the second layer. It's connecting neurons number 3 in the second layer to neurons number 1 in the third layer. So altogether, you every time you have a link between the neurons, so you will have like all those neurons are connected to each other, like they are all connected to each other like this. Every time you have a connection, then you will have a given weight, and those weights, we are going to write this like this as theta, where each theta has a superscript that writes that denotes the number of the layer, which layer does it refers to, and then the subscript denotes the pair of the neurons that are being connected by these weights. And this weights, again, is going to be very important. That's going to be the parameters of the model that is going to dictate how the values from each neuron is going to be transmitted, with which magnitude is it going to be transmitted to the next neuron. So those weights is the most critical part of the artificial neural network, and those are going to be, we will need to update those weights so as to find a way to map the input to the output. Like the way that the model is going to predict the value of the output depends on the value of those weights. So that's going to be a very important thing. So now if we try to just write down mathematically what this means, then it means that each neuron is going to take the values from the neurons of the previous layers, combine them to each other with the weights, add the bias, put this to feed that to the activation function, and then this is going to be the value that is used as an output. So let's take one example just to illustrate. If you take the neurons, the first neurons of the second layer, so this neuron here, the first neurons of the second layer, this neuron is going to take as input the values of each of the previous neurons. So it's going to take the neurons number 1, which is going to be the feature 1 from the layer 1. It's going to multiply it by the weights theta 1 1. It's going to take the neurons number 2 in layer 1 and multiply it by the weight theta 1 2 in layer 1. It's going to take the neurons number 3 in layer 1 and it's going to multiply it by its the weight of this connection. Then it's going to add to this the bias, so the weight associated to the bias that dictates how easy it is to activate these neurons. Then, so this is going to give you the value of z. So this is the variable z that we talked about. In this case, we are going to write this z in the second layers. This is going to be z1 in the second layer. This is z for the first neuron in the second layer, and then this z value is going to be fed into the activation function. The activation function will take as input the variable z, and this is what is going to generate the output that is generated as an output of the second layer of the second neurons, the first neuron of the second layer. So just to do another example. So now if you take this neuron here, this neuron, that what is gonna so this neuron is the first neuron from the third layer. It's going to take as input the bias. So the bias is gonna be the theta 1 from the second layer plus the weight theta 1 1 from the second layer and multiply it by the value of the first neuron of the second layer plus the weight between neurons 1 and 2 in the second layer is going to be multiplied by the value of the second neurons in the second layer, and then add to this the weight and the neurons number 3 in the second layer, like this. Okay, so it's gonna take all of this again, so that gives you the variable z. In this case, this is z13. This is the value that you get when you combine all the input signal from the previous layer. In this case, we are calculating the output of layer number 3. So the previous layer in this case is layer number 2. So it takes all the signal from the layers number 2. So for example, this one is becoming here, like each output of one layer is going to be used as an input from the following layer. And then this variable z is going to be transformed into by the activation function. It's going to be transformed into the output given by the model. In this case, now this is going to be the overall output of the model is going to be the output given by the last neurons. So this is the different step that is needed to understand how you start from this input layer. They are going to be transmitted to a hidden layer, and each hidden layer, each neurons of the hidden layer is going to generate its own output signal, which are going to be combined to each other, and that's going to be used to generate the output of the signal. So altogether, at the end, the output of the model is just a very complex function. It's going to be a very complex function of each of the starting inputs. It's just going to be a very complex function of the initial features. Like everything here can be, you can start by writing the output of the model as a function of the value of the second neurons, but then each of the value of the second neurons, you can write them in terms of the value of the first the neurons of the first layer. So everything, if you expand this function several times, then you will be able to express the output of the model in terms of the value of the initial features, but it just becomes a very complex function. Also, it becomes a very nonlinear function, because every time you have a g, then g is a nonlinear function. It can be a sigmoid function, a hyperbolic tangent, a ReLU function, a step function. So it becomes a very complex nonlinear function with a lot of parameters that relates the inputs to the output. And that's what allows the artificial neural network to map a complex relationship between input and output. So just like typically in machine learning, it's not convenient to write the relationship between input and output as individual numbers like this. It's going to be more convenient to write this in terms of vectors. So it's going to be better to rewrite this thing in terms of vectors. So let's see how this works. So in this case, we can define a series of vectors. For example, we can define a vector that contains the value of the output of all the hidden of the first layer, the values of all the first layers, the neurons of the first layers. So in this case, this input is going to be the values of the features like x1, x2, and x3. And in addition to this, you are going to add the bias on top of it. Okay. Then what you are going to do next is to define the same thing for the second layer. So you're going to define the values of all the input, all the values of the neurons in the second layer. So you're going to write the value of the values of the output of the first neurons of the second layer, then the second neurons of the second layer. Let me write this again. Okay, so this is the first neuron of the second layer. This is the second neuron of the second layer. This is the third neuron of the second layer. Then you are going to do the same for the variable z. You are going to define a new vector that contains all the variables z of the second layer. So this vector z is going to be the first value of z for the first neurons within the second layer, the value of z for the second neurons in the second layer, and the value of z for the third neuron in the second layer. And then this vectorial notation allows you to write the relationship of one layer to the next, how you go from the values of the neurons in one layer to the next in a more compact way. Because now what you can write is that how do you go from the vector in the layer number one. The first thing is that they are going to be transformed into the variable z by being mutually combined with each other, and the way that you're going to combine them is by multiplying with some weights. So for this, what we are going to do is to define now a matrix of all the weights that are used to combine the neurons for the layer number 1 to the neurons from the layer number 2. So now you have quite a bit of weights, and so that's why we're going to store it into a matrix. That's going to be a better format than a vector in this case, because you need to define the vector between each pair of vectors of neurons. So we're going to write this as a big matrix that looks like this, where the first element of this matrix is going to be the weight associated to layer number 1 between neuron 0 in the first layer to neuron 1 in the second layer. Then we are going to put the weight of the layer number 1 that is associated to how the first neuron in the first layer is connected to the first neuron in the second layer, etc. We are going to put the theta 1, 2, and then the theta 1, 3. So all the weights associated to all the connection. Then on the second line, we are going to put the theta of the first layer of that governs how the bias number 0 is connected to now the second neurons of the second layer, etc. So theta 1, which is going to be governing how the first neuron of the first layer is connected to the second neuron of the second layer, etc. So you're just going to put all the weights that governs connections between all the pairs of neurons between layer number 1 and layer number 3. And in this case, it's more convenient to write it as a matrix where each line is going to govern is going to refers to the number of the neurons in the second layer. So you have all those weights here are going to be associated to the neurons that are connected to layer number 1 to the neuron number 1 in the second layer. So this is going to be this first index 1, 1, 1. Then all those weights are going to be referring to the layer number 2, the neuron number 2 in the layer number 2. So this is going to be all those weights that are connected to this layer, the neurons number 2 in the layer number 2. And then the last line is going to be to all the weights that are governing the connections between the neurons in the layer number 1 to the third neuron in the layer number 2. So this one is going to be theta 1, 3. Then we have theta 3, 2, and then theta 3, 3. Okay, so this is going to be a big matrix like this that contains the value of all the coefficients of the model between layer number 1 and layer number 2. And once you have this vectorial form, then it's very easy to write how you go from one layer to the next, because now you can say that the variable z, the vector z in layer number 2 can be obtained just by doing a matrix product. What you will do here is that you will multiply the matrix theta, you will multiply it by the values of the neurons in the previous layer. In this case, you can do this multiplication because this one has four columns and this one has 4 lines. So you will take this times 1 plus this times x1 plus this times x2 plus this times x3, which is going to be exactly the same as this relationship here. So now just by writing this as a vector product, you can say that you take the matrix theta 1, you multiply it by the vector a1, and that gives you directly the variable z2. Now you have transformed the values of the neurons in the third layer. You have transformed them into the variable z in the second layer. And then the last thing that you need to do is to take the variable z2 to feed them to the activation function g, and this is going to give you the value of the second layer, the output from the second layer. So now you can summarize all those information just as two operations like this. First, you do a matrix product between the weight of the model and the value of the neurons from the previous layer, and then you feed that into your activation function, and that gives you the new output that is going to be used as input for the neurons into the next layer. So writing this as in a vectorial format first makes it more condensed notation, but also when you will be if you are actually coding those network either in Python or in MATLAB, coding them as network is going to be very critical, because you can do much more, you can do faster operation if you do it based on vectors. It's going to calculate all the values for all the elements of the vector all at once, especially if you run this on a GPU. It can calculate all those vectors, do an operation on all the components of the vector all at once. And GPU, for example, are very optimized to do some operation on vectors very fast. So it's going to be much faster if you code those calculations in terms of vectors rather than just writing a loop on all the neurons, or writing a loop on all the components of those vectors. That would not be a very efficient way. And writing it in an efficient way is going to be pretty important for artificial neural network, because it's quite computationally heavy otherwise. So you really need to make sure that your code is efficient. That being said, if you're just going to use libraries in MATLAB or in Python to just use those existing libraries to prepare your artificial neural network, then you don't need to worry about those implementation details. So now that you have set up your neural network, the question is, how is the neural network going to learn how to transform the input features into the output? How is it going to learn how to map the input to the output so that you can predict the value of the output based on the knowledge of the input features? So this is the process of learning. When we talked about the process of learning for the polynomial regression, so we talked about conjugate gradient, where the idea is that you start with some arbitrary values for the parameters of the model. You compute a cost function to see how well the model is doing, and then based on the cost function, you use the conjugate gradient, you calculate the gradient of the cost function with respect to the value of the parameters, and based on this you update the cost function so as to minimize, to find the right you try to find the right parameter that will minimize the cost function. So here it's going to be a similar idea in artificial neural network. We won't go into too much detail regarding how it's done in practice, but nevertheless the idea is exactly the same. In this case, the key thing, the process of learning for an artificial neural network will be to find the right values for the parameters. And you can have a lot of parameters in artificial neural network. So again, even if you take a very simple network like this, where you have 3 input neurons, you also have a bias, and those are going to be connected, for example, to 3 hidden neurons like this that are going to be connected to maybe another hidden layer, which is going to be connected to an output. For example, if you have something like this, where you have, in this case, your input layer has, we are going to write n1, the number of neurons in the first layer. So in this case, you have 3 neurons in the first layer plus the bias. Then then you have the second layer, which is a hidden layer. In this case, this second hidden layer will have 3 neurons plus 1 bias again. Then you have the third layer is also a hidden layer, and in this case it has two neurons plus in this case this is the number of neurons in the third layer. So there is two neurons like this plus one bias like this, and then you have the last one, which is the output layer, and in this case the output is the fourth layer, and there's only one neurons in the output layer. And then if we try to look at how many parameters, the number of parameters in this case, you have a parameter every time that you have a connection. Every time that you have a connection, you have a given weight. So this weight is going to count as one independent parameters. So if you look at first the number of parameters that you have in between the first layer and the second layer. So to get the number of parameters, you just need to count how many connection do you have. So for each neurons of the second layer, each neuron of the second layer is going to create a given number of connections. So to get the number of connection, you can start with the number of neurons in the second layer, and then you need to multiply this number by the number of connection that it needs to create. Each neurons here within the second layer is going to be connected to 1, 2, 3, and 4. It's going to be connected to those 3 neurons plus the bias. So you will get 4 parameters, 4 weights per neuron. So it is going to be, in this case, connected, the number of parameters is going to be n2, the number of neurons in the second layer, times n1, the number of neurons in the first layer, plus 1, where 1 is the bias. And then you will have the same for each of the neurons in the third layer. It's going to be connected to 1, 2, 3, 4 neurons. So the 3 neurons of the second layer plus the bias. So it's going to be the total number of weights that you will need to fix here is going to be the number of neurons in the third layer times the number of neurons in the second layer plus 1, where 1 is the bias. And then at the end you will get same thing, the number of the last number of connection that you need, which is going to be the number of neurons in the fourth layer times the number of neurons in layer number 3 plus 1 for the bias. So at the end it gives you a pretty high number of parameters. You can easily get hundreds or thousands or even millions of different parameter theta. So here when we say parameters, we're talking about all those parameter theta between each layers and between each pair of neurons. Those are the parameters that needs to be optimized. So the way that you are going to optimize these parameters, this is the process of learning. What the model is going to do is that you are going to be exposing to the model some examples. So you are going to provide some training example to the model. The model is going to learn by example. So you're going to provide a combination of different values of x together with the different values of the corresponding y. So those are the training example. This is supervised machine learning. So you have the input and the output together. You're going to provide all those training examples, and the model is going to try, based on those training examples, to adjust the values of the weights so that you can map as well as possible the features to the output of the model, like the observation y. And the way this is going to work, the way this learning is going to work is the same spirit as for a linear regression, is that you are going to define a cost function. The cost function j depends on the value of the parameter theta that you will be using, where theta is all those parameters here. So you have a complex cost function that depends on a lot of those coefficient theta. And this cost function, for example, can be some kind of mean square difference, where you capture how well the model is doing by taking the difference between the predicted value, the values that are predicted by your model for each training example, and you look at how different is it from the true values, the true output of the training example. Then you take the square difference to make sure that you cannot have some positive error that is counterbalanced by some negative error. Then you are going to sum over all the training examples. So you will use, for example, m training example. So you will take the sum between 1 to m of this, and then divide by 2m, for example, if you want to use the same cost function as for the case of linear regression. And so here, this value here, the y predicted, this is the output of the model. So this is the hypothesis of your model. This is the h of theta. This is the output of the model. And here you are just comparing the output of the model with the true observation from your training example. And based on this is going to give you an estimation of how good your model is. Like if this is the error of your model, so you do the sum over all the training example, you look at how good your model is. If your model is very good, then the training error will be very low. If your model is pretty bad, then the cost function will also be very high. And your goal will be to optimize to optimize the value of theta. So, and for this, your goal will be to minimize, to find the theta value, the value for the coefficient theta, so as to minimize the cost function. So that's what is going to be the goal. And for this, you can use the same kind of techniques than the one we used in linear regression. For example, the conjugate gradient method, although it's going to be a little bit more complicated. You will need to use some a little bit more complex algorithm like the backpropagation algorithm to find a way to change, to adjust the value of the coefficient theta of your model so as to minimize the cost function, and to have a cost function that is as close as possible to zero, where zero would be a perfect model that can perfectly predict the value of the output. So in the case of artificial neural network, there is one additional difficulty as compared to linear regression model, is that when you plot the cost function j of theta as a function of the values of theta. So theta is corresponds to all the coefficients of the model, theta 1, 1, theta 1, 2, theta 1, 3, and this is for each of the pairs of layers. So you have a lot of different theta. So it should be a plot in a lot of dimension, but here I'm just going to plot in just one dimension to represent what it looks like. In the case of linear regression, the reason we chose the MSE, the mean square error, as a cost function is because when you plot the cost function as a function of theta, it always gives you a convex function, which means that you can always find the minimum of this function by the conjugate, the gradient descent algorithm, or the conjugate gradient. Here, in the case of an artificial neural network, because it's a more complex nonlinear relationship between the input, the parameters, and the output, when you plot the value of the cost function as a function of the coefficient theta, then potentially you can get some more complex function, some more complex landscape for the cost function. This is the cost function landscape. It shows how the cost function, the error of the model, is changing if you change the parameters of the model, if you change the values of the weights in between the neurons, theta. If you change those parameters, then your model will become good or bad. So this is what you need to do. You need to change the value of theta in order to make your model as good as possible by minimizing the cost function. So for this, you can just use, for example, the gradient descent, which means that you will start just like the same for linear regression. You will start with an initial random guess for theta, and then you will calculate the gradient of the cost function with respect to theta. You will look at in which direction should you change theta so as to minimize the cost function. So in this case, you will look like the gradient tells you that you need to decrease theta. You always need to go towards the negative gradient. So in this case, if you look at the gradient here, you find that the cost function is increasing if you are increasing theta, which means that you need to decrease theta in order to go downhill to minimize the cost function. So you will do it like this. You will repeat this several times, and so you will end up here. But here the problem is that depending on where you start, for example, if you were to start at a different initial choice for the values of theta, then in this case you would find that the gradient is negative, which means that the cost function is decreasing if you increase theta, which means that you actually need, in this case, to increase theta to minimize the cost function. You always go in the direction of the negative gradient. Now you will end up to this minimum. So it means that depending on where the choice of your initial guess for the values of the coefficient theta, you can end up in a different position at the end. You can get stuck into some local minima. So this one would be in this case, the global minimum. So the real minimum, the real value, the best possible values of theta that gives you the best global minimum. This one is a local minimum. So in this case, you can have different types of minima depending on where you start. So it's typically not a big problem in practice for some reason that are not fully clear. But nevertheless, like artificial neural networks are typically pretty good at avoiding those local minima and still find some a good final set of parameters that gives you a low value for your cost function. But nevertheless, typically if you train your neural network with different initial guesses, you will most of the time arrive at different values. Like the minimum that you will find for the cost function will not be the same, which means that the values of your coefficient theta that you will get at the end of your minimization will be different. Usually, that being said, it's not going to be a big problem because usually you will always find some minimum that are pretty good, not too far away from each other, but you might get a different answer every time you retrain. So it's always a good idea in this case to try to train the model several times to make sure to try to train it several times by starting with different initial position to make sure that you end up with a model that doesn't get stuck into a very high local minima. Like for example, if you happens to get stuck here, this is a local minimum as well, but in this case this would be a local minimum that is associated with a very high cost function, which means that if your model gets stuck here, then it would not be very accurate. It would give you a very high error. So in this case, to avoid this, you just need to repeat several times with different initial values for the weights to make sure that it doesn't get stuck into a very high local minimum. So to summarize, those types of artificial neural network are very popular nowadays because they have a lot of good attributes that make them suitable and very efficient to build some powerful machine learning model for regression or also for classification, to classify between different classes. But nevertheless, they are not always the best option, especially sometimes for engineering problems. Sometimes just linear or polynomial regression or lasso will just be better or more simple option than the artificial neural network. So just to summarize the strength and the weakness, or the pros and cons of artificial neural network, especially as compared to linear regression. So in terms of the pros, so in terms of the strength of artificial neural network, like the real very important strength is that it can create its own features. So this reduces the need for feature engineering, because it can just create in the hidden layer the feature that it wants. By combining the inputs together, it can just create its own new features that you would not necessarily have thought yourself. It's just going to create it on its own. There is no need for intuition. The second thing is that it, unlike linear regression, it can model complex nonlinear hypotheses. So depending on the activation function that you use, it can model, it can handle very complex, especially nonlinear hypothesis for your model. So you can have some very complex relationship between the input and the output without the need for creating new features that are x square, x cube, etc. The drawback of artificial neural network, like the weaknesses, the possible weaknesses. The first thing is that it's typically slower to train than polynomial regression. It just involves more computing time to train, because you have much more parameters. So it takes more computing time. So it's typically slower to train and to use than linear regression. So that's something that sometimes you may want to favor linear regression just because it's faster. So it's always something good to start initially, because it's just faster. So it's easier to get started with this and to do some quick tests. The other major drawback as compared to linear regression is that it needs a lot of training data. If you don't have several thousands of data or hundreds of data, then it's going to be very challenging to use artificial neural network, because there is a lot of parameters in artificial neural network. So since there's a lot of parameters, you need a lot of data. The minimum number of data that you need for an artificial neural network, there is no like a fixed rule. It depends on the types of data that you have. It also depends mostly on the number of dimensions, the number of features. If you have just 2 or 3 features, then maybe you don't need that much data. Maybe just hundreds data might be enough. Typically, a good rule of thumb is that you need 5 or 6 data per dimension. So where each dimension is a feature of your model. So if you have a given number n of features, then you need at least, let's say, 5 or 6 times the number of features as a number of training data. But if you have hundreds or thousands of features, then you will need potentially millions of data, because you will need to have enough data to fix the value of all those weights between all the connections of the input of the neurons between each of the layers. So you have a lot of parameters to fix all the values of the theta. So you really need a lot of training data, and sometimes you just don't have enough training data to conduct this training. So especially when you are using deep learning, so when you have more than one layer, when you start to have 2 hidden layers, 3 hidden layers, 4 hidden layers, the more layers you have, the more complex your model can become, because it can start to create its own simple features in the first hidden layer, and then combine those new features to create even more complex secondary features. So it creates more and more complex features as you go deeper and deeper within the network. So it can become very powerful, can find some very complex relationship between input and output. But for this, in order to train, to find the right value for all the parameters, in order to train your network, make it able to learn the right way to convert the input to the output, then you will need a lot of data to be able to find the right value for all those coefficients. So if you don't have that many data, then it's going to be very challenging to use an artificial neural network, and in this case, probably using linear regression, polynomial regression, or lasso might be a better case. And the last disadvantage of artificial neural network is that it's pretty much a black box. It has a very low interpretability. And by that I mean that when you are doing polynomial regression or linear regression, then it's very easy to understand what the model is doing. You get a linear relationship between the input and the output. You can look at the values of the coefficient, the linear coefficient, and those the value, for example, if you have a y equal ax plus by plus c, if y and x are normalized, then the values of the coefficient a and b, you can interpret this. It gives you a simple mathematical formulation. The value of a and b gives you the weight of the variable x and y, assuming that they are normalized. So this allows you to understand which one of those two features is the most important. Like the higher the value of this weight, the more important the feature is. So in this case, you can really understand what the model is giving you. This would be a very interpretable model when you are just using linear regression. When you are using artificial neural network, it's almost impossible to understand what the model is doing. It's going to come up with its own features that are very much non-intuitive. If you just directly look at the value of the coefficient theta 1, 1, theta 1, 2, theta 1, 3, etc., you cannot understand anything about those values. It doesn't tell you any useful information. Actually, when you train an artificial neural network, you cannot even know which features is the most important or which feature is not so important. You don't get any new knowledge from the model. It gives you an answer, but it's very complex to understand why it gave you this answer. Of course, it's just a very complex equation, so that relates the output to the input. So it's just a giant equation, so there's nothing mysterious. It's not black magic, but nevertheless it's an equation that is so complex that it's very hard to understand what it actually does, or to get some intuition about why it's working, or to get some intuition about the nature of the output that it's creating. So it's typically going to work, and it's usually going to work well, but it's going to be a very low interpretability, which means that sometimes it's going to work and sometimes it's going to fail, and you will not be really able to understand why, because it's just very hard to understand what happens inside an artificial neural network, like the way the input, the values of the input are transmitted to the different neurons and are combined to each other into an output, is something that is very non-intuitive, and that is very hard to understand when it goes right or when it goes wrong. It's very hard to understand why the artificial neural network made this given prediction, why to understand why it got it wrong for this specific case. So this is a problem sometimes when you need to understand, to not just an answer, sometimes your goal is not to get only an answer from a model, but to also have some reliability to be able to understand why the model gave you this answer. And in this case, if you need to understand why, then the artificial neural network is typically not going to be a good choice, because it cannot explain why it made each prediction. That being said, if your only goal is to get a very accurate network, then artificial neural network, and especially deep learning, if you have a lot of data, is going to be a good choice, because it's a very flexible model that can very often give you, assuming you tune well the model, that can give you a very good answer. The process when you are when you will be constructing an artificial neural network, so just like any model, you need to tune the hyperparameters. So in the case of linear regression, a polynomial regression, like the hyperparameter is just the maximum polynomial degree that you are considering. In the case of lasso, the hyperparameter is the value of the regularization coefficient lambda, and depending on how you tune those hyperparameters, you can have a model that is underfitted or overfitted. So in this case, for artificial neural network, the hyperparameters will be, more importantly, how many layers, how many hidden layers are you using. The more hidden layers you have, the more complex your model becomes. So it can become very accurate, but it can also become hard for the model to generalize, so it can become overfitted. And on the other parameters will be the number of neurons inside each layer. If you use, even with a single hidden layer, if you use a lot of neurons, then potentially it can become a very complex model that can also be overfitted. And on the other hand, if you use just one single hidden layer with just one or two hidden neurons, then most likely your model will not be complex enough to properly interpolate the training set. So it's going to be very difficult for the model to map the input into the output, and in this case the model is going to be very likely overfitted. So it's the process of tuning those hyperparameters, so how to choose the number of hidden layers and the number of neurons, is going to be pretty much the same process as what we did for lasso or for polynomial regression. You need to separate the data to keep a fraction of the data that serves as a validation set. You need to take your data sets, separate it into the training set that you are going to use to train the model. Let's say 80% that is going to be used to train the model, and then 20% that is going to be used as a validation set. Or you can use the cross-validation. And the idea is that you will keep those data invisible to the model. You will not use those data to train the model, and you will use those data to check how well the model is predicting. And you will check, for example, you can calculate the mean square error that your model is doing for the validation set, and then you can do this for different number of neurons. And most likely you will see that if you use too few neurons, then you will get a very high error because your model is just too simple. It is underfitted. Then if at some point there will be an optimal number of neurons, and then either it will just plateau, either it will just start to increase again when the model becomes too complex. So too few neurons means that your model will be underfitted, and too many neurons will be that your model will be have a high variance, so it's going to be overfitted. So it's the same idea. You will try different number of neurons, different number of layers, and see which one gives you the lowest error for the validation set, to see whether you can have a model that does not have a high bias but doesn't have a high variance as well, to find the best balance between underfitted and overfitted. So it's very similar ideas as for the other machine learning model that we have seen so far for regression. You will need to tune the hyperparameters to make sure that your model is not too complex and not too simple as well.